groundwater. So we are saying that the flow of groundwater is known to be through the interconnected space. What this simply means is that if I have any rock mass, it has got interconnected spaces, pore spaces within, like these sections. And it is through these sections that water is capable of flowing through the rock. It is not like the usual pipe we have or an open space where water could freely flow. But then in terms of soil, it flows through the various particles that exist within the soil. The various particles, the tiny particles that make up the soil, it is through which we are going to have our water to flow through. And when it comes to rock, like a rock mass or an intact rock mass or a rock material, it is through the various discontinuities. If I may take you back, for example, let's have a look at this. Good. So assuming this is a rock mass we are looking at, water will be able to flow through this rock mass through the interconnected spaces. Other than that, it will find it difficult to flow. It is through these spaces that water is capable of flowing and nowhere else. Good. So often the flow of groundwater through a confined or unconfined porous material can be presented as a uniform flow. So since water flows through tiny pores within the rock sample, it has not got that flexibility to flow in a turbulent manner, as you would see in rivers and then water that overflows a dam. You don't see that same situation when we are talking about flow through rocks or soil. And so the flow, we would say, is uniform because it's finding its way through gradually. And then the term seepage flow is used to describe the movement of water through or under soil structures to wells, drains, and reservoirs. So generally, the Reynolds number defined in fluid mechanics is less than 1, and therefore the flow is laminar. We say a flow is laminar. I have some images here to show this. So if we are talking about laminar flow, this is what we mean. This. So if I have any water that is flowing in a uniform direction like that, they are not, the parts of the various water particles are not crisscrossing. But if it were to be turbulent, this will be the nature of the flow of water. And this one, you don't even seem to see the direction of it. It flows anyhow, crisscrossing each other. Good. So that is one of the assumptions we make when we are talking about flow through water, that it is laminar and not turbulent. And once we say the flow is laminar, then we could use Darcy's law, as we could term it as a valid situation, or the law is valid in this situation. So a simplified theoretical and numerical approach is developed. Flow through water, for example, if I have a rock sample that has got various, for example, let's say there's a dam and I have soil here throughout, and then there's flow through it, the water will find its way. So let's say I have done some embankment here for it. The water will find its way. So let's say there's the water sitting here, and then the whole of this section is the soil. And then there's soil all over this section to a lowland. Water will still find its way to travel through. If there is that possibility for the water to escape, it will find its way through this soil and find its way here. So there is this theoretical concept that people have come up with, and researchers have come up with, which we call the flow net. And that is these lines. You would have to calculate for the flow along each of these lines, and it's some kind of a simplified approach to doing this calculation. But then that is purely soil mechanics and is beyond the scope of this topic. And so it's just for you to know that there is an approach to computing for the flow of water below dams, embankments, and whatnot. And then this is followed by the description of test methods. So we could also conduct a test in the laboratory to find out the flow of water through a given material. So let's say you are operating a surface dam, a surface mine. You have a fair idea of your rock properties. You've been able to define the strength and whatnot. But then you know that there are other factors like water that is capable of undermining the strength of your rock. And so you could go ahead to see, assuming there is a river nearby, what is the probability or the likelihood of the water within that river finding its way into your pit? And so you want to conduct a test with this rock sample or the soil sample, whatever, and then come out with the probability or the coefficient. We call that the coefficient of permeability, the ability of that rock to transmit water or to allow water to flow through it. And that will give you a fair idea what you should do, whether there is the need for you to drill a well nearby that will be trapping the water that will be seeping through the rock, or what decision would you take? That is when you now know these values. Or the hydraulic conductivity. It gives you an idea of the gradient, whether your pit is below and the dam or the river we are considering here is uphill. You could know these properties within the lab through experiment and then use that for your judgment in the field. Then water flow through soil or rock in various ways depending on the nature of the ground. Yes, it's a factor. Then water transmitting soil or rock units are called aquifer. So let's say there is this rock that is more or less the producer of water. We call that an aquifer. It allows the flow of water through it. It contains water. And these are the ones that usually we call the, the spring and whatnot. Depending on how the water will be dashing out of it, we could give it a name. And so some of the flow, the groundwater flow through these aquifers by using the intergranular spaces within the rock as the way of flow. Others flow through fissures and some also through conduit. So if we want to demonstrate this by images, we could have this. So let's have a look at these images. So a fissure is any crack within the rock formation. So, and if this rock were to be a rock that contains water, if there's that ability of the water to come out or flow, it will be flowing through these fissures as this. And then we have one we call the granular. Intergranular means that the grains within the rock sample are distinct, such that you could, when you look at it, you could see the various grains, aggregates that have come together to produce that given rock mass. And so the water will find its way through these grains to flow. And that is intergranular flow. And then we have the last one, which is the conduit flow. Conduit flow here is that where there is that distinct cut, as if there's this pipe, okay? You've kept something like a pipe within the rock, and then all the water is descending through it and then finding its way below. And that is a conduit. So figure 24, we will get to it, shows the flow of water through a tube of soil. So this is the figure. So let's say there's that possibility where we have a PVC pipe. We cut a PVC pipe, fill it with soil, okay, or grains of a rock, and then we place it inside this tube and allow water. That is the kind of test we conduct in the lab. Then we allow water to find its way through the grains, and that will help us know the ability or that permeability constant, coefficients of permeability of the various particles that exist within the soil. And so when this is the case, before the water could flow, there should be that difference in elevation, okay? So we have this, assuming the water is on a higher elevation and there's another one at a lower elevation. We measure this difference that you see here, and we call that the total head. It is this difference in pressure in terms of the water level is what is causing the flow within the soil sample. And then we have this as the elevation, how high I have risen this particular tube from our reference point. So this is our Z, this is the total head, okay? And that is what, and we also have something we call the velocity or the pressure head. So we are looking at the pressure with which the water is flowing through, coming out of the soil. So we'll consider that one too. And we have the Q, which usually we refer to as the quantity of flow or the rate of flow of the soil. So we have the water level at each point is presented by its distance. So for example, from an arbitrary datum, and it's referred to as the total head. So according to Bernoulli's equation, we have this as the total head. Other books will represent it with capital H, others will say small h, or change in h, whichever the case. We are saying change in h because we are looking at this height, and then we are taking it from the total of this whole height. The difference that is there is what we call the change. Good. And this is the elevation head, how high we have risen the tube, this particular tube, soil sample we are considering. How high is it from our reference point? And then this is a component that is talking about the pressure, the water pressure. Water itself exerts pressure. So assuming if it were within the ground, we are considering the water has pressure within the rock. So we are considering this. And this is the unit weight of the water itself, and the pore water pressure is this. So we are considering that one too. So the pressure head is equal to the pore water pressure on the unit weight of water. And then this other component is referring to the velocity of flow. But we have just stated that the flow of water through rocks is only possible through the various pores. And this flow is such that you can't even see sometimes. All you see is that you have seen water in the sump, but you don't seem to find out how the water is flowing. As if it were a river, you would see that this is how fast the water is flowing. But in the case of mines and in our situation as mining engineers, we only see the water seeping out gradually. And so it is impossible for us to be able to predict or see visibly how fast it is flowing. And so usually if we are considering this or adopting Bernoulli's equation, if we are adopting Bernoulli's equation into our field, we say this velocity head, we don't need it. It is negligible per theory or per literature. We say this is negligible. The velocity head is negligible. It is not considered. So let's then move ahead and see. So the formula then finally becomes this. If we are talking about flow of water or flow of fluid through soils and rock, then the next thing we need to consider is the gradient. You know, when you look at this diagram, the thing is tilted in a way. So it's just like you finding the gradient of a straight line. You want to find out the gradient of this line. And that gradient will consider the length of the soil. It is considering the length through which the fluid is flowing from one point to the other. That length is being considered. And then the pressure head with which it is causing, or the total head that is causing this flow. So if I have my total head on my length, literature is saying this is proportional. And so it is equal to the I. Okay, so my change in head is directly proportional to the length or the distance of the soil, the travel within the soil sample. So assuming I fetch a soil sample and pile them here, and I want to consider the flow of water through it, I'll only look at this section to that section where the pile of material is. This is defined as the length. And then the angle, the total head that is causing the flow, or the total energy that is pushing the flow, is the change in H. So literature is saying that this change, or the total head, is directly proportional to the distance, that is the length of travel. And we denote that with a constant if we are introducing an equation. So we say that this I is equal to the change in H on my L. And that is what is stated here.